All right, so welcome to another fun-filled week of statistics. Man, it's flying by. As soon as this week's done, we're done with January, believe it or not. So today's plan, obviously, like we always do, we're going to go ahead and I'll open it up to homework questions and we'll talk about homework stuff that's out there. And then we're going to keep marching on talking about probability density functions. We're going to specifically talk about a few different types. We're going to start with the binomial and then talk about the geometric and then the Poisson and kind of move our way down. But again, these distribution functions, these are how we're going to actually determine probabilities, likelihoods, so that when we're given information, we know how to interpret it. Like, what does it actually mean when we go out and we do a study and we find out, you know, that 10 of the 25 people that we looked at approve of the college president, right? Is that likely? Is it unlikely? We're going to be able to kind of answer those questions. So that's the goal. I do want to mention a couple things before we get to homework, just because if I don't mention this, I'm going to forget. I guess I said I was going to mention a couple things. It's really one thing. The project, remember project one is due on Thursday. Well, I have changed that. I actually extended it to next Tuesday. So you still have a week to complete your project instead of just 2 more days. It seemed like people didn't really have enough time and everything. So just so you know, the due date for that is now February 2nd. All right. So it's not the 28th of January, it's February 2nd. So it has been updated in Canvas. If you look at the Canvas calendar and the due dates, it's there. But I want to get it out here so everybody knows. So if you're still working on it, which everyone should be still working on it, I just got you 5 more days to do it. Now, just realize that we also have an exam next Thursday, and the exam next Thursday is still going to happen. I didn't really want the project due the same time as the exam, but this still, I think it needs to be this way. All right, so still realize that there will be an exam a week from Thursday. That means this week there's not going to be a quiz. There wasn't a quiz scheduled, so there's still not going to be a quiz. So Thursday will be just a normal class, but I'll remind everybody about that at the end of today. All right, so with that, let me turn it over to you guys and let me ask you what homework questions you have, because I know a couple of you do. So either put it in the chat box or speak up and let me know what you'd like to look at.
Right. I was having issues with question 14 on the chapter 3 probability add and multiply. I couldn't figure out how to do conditional probability.
Okay, so which numbers were those again, Ashton? I'm sorry.
It was 14 of chapter 3
Okay.
probability add and multiply.
Okay, cool. And Willie put a couple in the chat box from that same section, numbers 5 and 9. So we'll definitely go look at those. Any others that we'd like to look at? So another one from that section as well. All right, ceremony number 17. Got it. And lady would like to look at number 29. All right, and then 4 from the same section. That's a question, sir. Yeah, okay, thanks, everyone. All right. All right, so it looks like we need to spend a little time talking about the adding and multiplying probability stuff, which means we're really looking at the ors and the ands and the conditional and all that. So let's go look at that. We'll spend some time, see if we can make some sense of it. So let me go ahead and share my screen and we'll go take a look at those. All right. So the first one on my list looks like number 4. Okay, so let's see what this says. It says, with one method of a procedure called acceptance sampling, a sample of items is randomly selected without replacement, and the entire batch is accepted if every item in the sample is okay. All right, so it says the ABC Electronics Company has just manufactured 1,950 rewrite CDs and 50 are defective. If 4 of these CDs are randomly selected for testing, what is the probability that the entire batch will be accepted? All right, so my first comment on this is read-write CDs. What the hell, do we even use those anymore? I mean, I know I'm old, but I'm not that old. I know better than using CDs. Anyway, all right. So think about what we need for this batch to be accepted. We need the 4 CDs that we randomly select to be okay, right? So the first one's got to be okay. The second one's got to be okay. The third one and the fourth one, both, they all have to be okay. Now, in order to do this, what we really need to do is think about, well, what's the probability of the first one being okay? And then if that one's okay and we don't replace it, what's the probability that the next one's okay, and then the third and the fourth? All right, so let me go back to a whiteboard and let me kind of walk you through how I think about these things. Let me clear all this stuff. All right, so here's my thought process with these. We've got 1,950 CDs, right? And there are 50 are bad. So let's think about getting that first one, right? So what we need 4 good ones, right? In order for us to accept this sample, we need all 4 of these to be good. All right, so let's think about CD number 1. What's the probability that CD number 1 is good? Either put in the chat box, yell it out to me. What's the probability that this one's good?
One out of 50.
Okay, so 1 out of 50 is a good guess there with Ashton. How'd you come up with that?
Well, because CD number 1 and then 50 are bad. So to find 50, you have to like count it all in the batch, I guess.
Okay. Well, let's think about this though. I don't want to use the bad number really, because I'm looking for a good one, right? So let's think about how we calculate probabilities in general. So think of it, this is our event. Our event is drawing or pulling out a good CD, right? That's our event. So we need to know the total number of possible outcomes, which would be the total number of CDs. And we also need the total number of good CDs, because that's our event. And so I see Willie actually just put this in the chat box. The probability of getting a good one, there are 1,950 good CDs, or there are 1,950 CDs, period. And out of those, there are actually 1,900 that are good. I took away the bad 50. So if I just randomly pull 1 CD out of this stack, this is the probability that it's actually a good one. 1,900 out of 1,950. All right. So again, the structure on this fraction, this is the total number, and these are the good ones. If I was looking for the probability of getting a bad one, it would be 50 out of 1,950, because there are only 50 bad ones out of that total 1,950. So we do need that 50 number, but really we just need that so that we can take out those, remove those bad ones to figure out how many good ones there are. So there's the probability that CD number 1 is a good pick, or is a good one. 1900 out of 1950. So pretty likely, actually, that we're going to draw a good CD. Okay, so now let's go to CD number 2. So we just pulled out a good CD, right? Because remember, that's what we're trying to do. We're trying to get 4 good ones. So I just removed a good CD. I don't put it back because this is without replacement. So how many CDs are left? How many total CDs remain now that I took one out? All right, so I just subtract one off. So it's going to be 1949, right? There were 950. No worries, Ali. I can tell you were on the right track. There were 1950. I removed one of them. So now there's 1949. Okay, so our total number has decreased because we removed one and we didn't put it back. All right, how many good ones are still in there? What's the number that's going to go on top? All right, good. A couple of you are throwing in here 1899. So it's not 1900 anymore. It's only 1899 because we just took out a good CD, right? What we're looking for, the event we're looking for is every one that we pull out is a good CD. So I just pulled out a good one, which leaves me one less good one to draw. And there's also one less total. Okay, well, we'll keep doing this. So we just pulled out 2 good ones. So we're going to go remove a third disk. Well, now there's only 1948 total disks because I've already removed 2. And in terms of the good ones, there are only 1898 because we've already removed 2 good CDs. And then if we go to CD number 4, you can see that the process is just kind of the same. We're just subtracting 1 from each of those numbers. So by the time we get to the 4th CD, this is our probability. That's the probability that it's still, that we're still drawing a good one. All right, so before we go any further, how are we doing on these 4? Do they make sense? Are you understanding why the numbers are going down by 1? I just want to make sure there aren't any questions at this point. Okay, and this is all because we're not replacing. If we were replacing, the numbers would not change, right? I pull out that CD, I test it. Hey, it works. I put it back in, and I still have the full number of CDs. I still have the full number of good CDs. And so that probability would not change. But this is because we are not replacing. We're changing our probabilities. Okay, so now the question is, what's the probability that all 4 of these happen? Well, this is where we multiply the probabilities together. This is the probability of A times the probability of B times the probability of C, and so on. So we just need to multiply these 4 numbers. All right, so I'm going to crack out my trusty TI-89 because I cannot do this in my head. Well, I could work it out, but nobody's got that kind of time. All right, so 1950 times 1949 times 1948 times 1947. Okay, and I ended up getting, as a decimal, 0.94399846117. Okay, so that's as many decimals as my calculator gives. But I'm going to round that to a relatively nice number, and I'm going to change it into a percentage. I'm just going to round it to 94.4 because 3998 is awfully close to 4. So if there are 50 bad CDs in this, and I randomly grab 4 of them, there's a 94.4% chance that all 4 of them are good. Okay, so that means that there's a 5.6% chance that at least one of them is bad. But that gets us to our answer. So the kicker to this one is no replacement. Super important to notice that there's no replacement because that makes those numbers go down. All right, so how is that for number 4? I have zero clue who asked me about that one at this point, but
thank you.
All right,
super
you're welcome.
helpful.
Awesome. All right, so let's go take a look at number 5. See what that one has to say. All right, so when doing blood testing for a viral infection, the procedure can be made more efficient and less expensive by combining partial samples of different blood specimens. If samples from 5 people are combined and the mixture tests negative, we know that all 5 individual samples are negative. So find the probability of a positive result for 5 samples combined into one mixture, assuming the probability of an individual blood sample testing positive is 0.1. All right, so yeah, I don't know if you guys have figured this out, but we're starting to run into word problem land, right? Here's the deal about stats. Stats is almost all word problems. So you're welcome. No, don't blame me. I didn't make this stuff up. But when we are actually applying things to the real world, they end up being word problems. So let's see if we can figure out what's going on now. So we're going to go and we're going to sample 5 blood samples, or take 5 blood samples, right? So we're going to grab 5 of us in this class, take the blood samples and mix them all together. Okay, now what we do know is the probability of any one of us testing positive for the virus is 0.1, 10%. So there's a 10% chance you take my blood, 10% chance that I've got the virus. So let's just call it COVID, since that's the virus we're all thinking about these days. So let's say there's a 10% chance I have COVID, right? But now we're going to go and take blood from 4 of the rest of you, right? So I'm just going to take names I see right here. So Ashton, we're going to take Ashton's blood and Branda's blood and Willie's blood and Carson's blood. Okay, so each one of those also has a 10% chance of being positive. So the question is, once we all get together, what's the likelihood that this total sample is positive? All right, well, we're going to actually attack this the same way we did the other one, where we're going to do that multiplying of probabilities, right? So, but here's what I'm actually going to do. I'm going to think about it in terms of negative. I want to think about what is the likelihood that this thing tests negative. And there's a reason I want to look at it this way, because in order for the test to turn negative, come out negative with the blood mixture, is if I'm negative and Willie's negative and Branda's negative, and right, like we all need to be negative. The problem with looking at positive is any one of us could be positive, and it's positive. All 5 of us could be positive, and it's positive. Like there are way more possibilities to get a positive result, right? Any one of the 5 of us, 2 of the 5 of us, 3 of the 5 of the 4 of the 5 of the, I mean, there's a lot of different possibilities. But for it to turn out negative, it has to be all 5 of us are negative. So I'm going to look at what's the probability of negative test for COVID. All right, well, if it's a 0.1 probability for positive. What is it for negative? All right, thanks, Willie. It's 0.9. How'd you get that? If you don't mind sharing. How'd you get 0.9 for the negative probability? All right, so you subtracted it from 1. Because remember how probabilities work. Probabilities have to add up to 1. And in this case, there are only 2 possibilities. You either are positive for COVID or you're negative for COVID. Those 2 events, their probabilities have to add up to 1, right? You can also think of this, we call that the complement. Don't know if you remember that term, but this is the complement. The complement of positive is negative, and we know that probabilities of complements add up to 1. All right, so there's a 0.9% chance that I'm negative. But that also means there's a 0.9% that Ashton's negative and Branda's negative, and so is everyone else that I said we're drawing blood from. All right, so let's think about the probability that we're all negative. Well, there's a 0.9 probability that I'm negative. There's a 0.9% probability that Willie's negative, Branda, Ashton, and I think I said Carson was the other one, right? So what we're going to do is we're going to multiply all those together. So again, I'm going to take my trusty T89 because I don't know what 9 to the 5th is off the top of my head. So this ends up being 0.59049, or around 59.0%. And I am going to put that 0 there just to sort of show where I rounded. I rounded to the nearest tenth, actually, instead of the nearest whole. All right, so it's only about a 59% chance that this thing turns out to be negative. There's a 41% chance that there's going to be a positive result. So I would say that this method is probably not a good one for these probabilities, right? The fact that 2 out of every 5 tests would show us that one of us is positive, that's not going to do very much good to try to speed up the process, because 2/5 of the time we're now going to have to look at each sample individually. You might as well just do them all individually in that case. But if it's a less likely chance that you're positive, like let's say it was just 1%. So check this out. What if it was 0.01 for positive? So there's only a 1 out of 100 chance that you're positive. So there's a 99 out of 100 chance that you're negative. Now, if we were to do the same thing where we mix all 5 together, you get, if we take 0.99 to the 5th, that's 95.1%. And there, you're not going to have to do individual tests very often, only 1 out of every 20 times. So I'm certain that this is something they actually do. I've never done anything in the medical field, so I can't speak from experience. But it seems to me like this would work really well if we're talking about something where the probability that you have it is pretty low. So, but like the last one, notice what we're doing is we're multiplying the numbers together. So Sirmani, I see your comment in the chat box. Let me go look at my question and see what it's asking for, because. All right, so find the probability of a positive result for 5 samples. What did we just calculate? What was that 59%? Yeah, that was the probability of a negative result. So how are you going to get the probability of a positive result from our negative result? Yeah, you're going to subtract it from 1. Okay, so this actually really illustrates how you have to be careful. You have to really pay attention to what's being asked. Wording matters. And what we talk about later today, when we talk about like the binomial distribution, stuff like that, wording is extremely important. You change the wording just a little bit and you end up getting completely different values. So I'm going to guess that that's why you had an issue, was you didn't subtract it from 1. There's also the potential issue of the 4 decimal place accuracy. Right? Also watch for how close you need to round. All right, so is that better for 5? Does that make a little more sense? Again, the idea is you take the probabilities and you multiply them together when they are independent, right? And the probability that I'm testing positive for COVID is completely independent of Branda, right? Especially since we're not in physical contact, we're not close to each other physically. As far as I know, COVID doesn't spread through Zoom. Oh my God, could you imagine if we had a disease that spread through Zoom? That's when we just say, okay, fine, we'll let the Terminators win. Anyway, so they're independent events. We can just multiply them together. All right, so that was number 5. Let's go take a look at number 9 real fast. All right. So giving a test to a group of students, the grades and gender are summarized below. So here's we call this a contingency table, right? And so we see that the males, there were 25 males who took this test, right? 25 males, and the breakdown was 3 A's, 8 B's, and 14 C's. And there were 24 females who took the test, and their scores were 4 A's, 11 B's, and 9 C's, right? So that's what this column is telling us. This row is telling us the total number of A's, B's, and C's. So in our class of 49, 7 people got A's, 19 got B's, and 23 got C's. All right, so good news, nobody got a D or an F. All right, everybody passed. But now let's see if we can calculate the probability. It says if one student is chosen at random, find the probability that the student was male and got a B. Okay, so remember what and means. And means both of them occur. So we want to look at this class and we want to count up how many males got B's. All right, well, their contingency table is awesome because it gives us that. That's this number right here, right? It's the number of males who scored a grade of B, and that is 8. So we know that there are 8 of them that got a B. So in terms of our probabilities, remember we need to know how many ways does our outcome happen divided by the total number of outcomes. So that 8 is the number of ways our outcome happens, that they're male and got a B. In terms of the total number of possible outcomes, well, that's this number down here in the corner, which is 49. So the probability for this one, I'm just going to type it in here. I don't know if it's going to give me the answer, or oh no, it says it needs it as decimal. But I'm going to take 8 and I'm going to divide by 49. Because there were 8 students who are male and got a B out of the total 49. All right, so that's going to be what it's going to be. I actually want the points. So let me see what I get here. 0.163, how many decimals did I say? 4 decimal places. Okay, so it's 0.1633 if we round to the 4th decimal place. Oops. All right, so submit my question. Yay, score on my last try, 1 out of 1. I got the green check mark. So contingency tables are your friend when it comes to these. It makes it a lot easier to find the information that you need, especially when you start talking about ands and ors and givens and stuff like that. All right, so good for number 9. All right, so Ashton, I don't know what's going on with yours. It could be a decimal issue. Most likely it's a decimal issue. If you want, maybe after class, I can look specifically at yours. I can pull it up and we can look. So, and just so you guys know, a blanket statement, I'm not going to always know why your thing is saying it's wrong because I can't see it. So it's totally cool to tell me that. Just don't necessarily expect an answer to why you're getting it wrong specifically. Because if I'm not looking at your specific one, I can't tell you. Okay, so just realize I'm not blowing you off. It's just I literally cannot do that right now. Oh, okay, cool. You just put something in wrong. Oh, no worries. You don't have to apologize. In fact, I'm glad that's all it was, because then it's a little bit, then I know there's no issues really. User error is, while annoying when you're the user, as a teacher, I would much rather have user errors like inputting stuff, because that means you're getting the process right. You're just typing something in wrong. All right, so let's look at number 14. All right, so we got Pew Research goes out and asks 1,306 Americans, from what you've read and heard, is there solid evidence that the average temperature on Earth has been getting warmer over the past few decades or not? Table shows the distribution of responses by party and ideology, where the counts have been replaced with relative frequencies. All right, so this is a contingency table, no different than what we had before in terms of the idea behind it. But there is one significant difference, and it's that last sentence, right, where it says it shows the distribution as relative frequencies. So instead of knowing how many conservative Republicans said the Earth is warming, right? We don't know that. We do know what portion of our sample were conservative Republicans who said the Earth is warming, right? So that 0.11, that 11%, that just says that 11% of the people that responded are conservative Republicans who said the Earth is warming. The next number over, the 0.2, that's 20%. That 20% means 20% of all the respondents said or were conservative Republicans who thought the Earth was not warming, and so on and so forth. So when we read these numbers now, think of them as percents, right? Move the decimal 2 spots if you want to think about it as percent. So like this total, 0.33 means that 33% of the people that we talked to were conservative Republicans. 13% were moderate or liberal Republicans. 34% were moderate or conservative Democrats, and 20% were liberal Democrats. These numbers tell us how many people thought the Earth was warming. So 60% of the people that they talked to thought the Earth was warming. 34% think it's not warming. 6% don't know. Okay, so let's see if we can answer our questions here. So the first one, oh my gosh, we have so many parts to this. Let's start with, are believing that the Earth is warming and being a liberal Democrat mutually exclusive? So let's backtrack. What does mutually exclusive mean? I know somebody's got to remember. What's it mean if two things are mutually exclusive? All right, that's close. Right, like I said, Ashton just put in there, they occur at the same time, but it actually is they cannot occur at the same time. All right. So the question is it possible? Did we ever find somebody who's a liberal Democrat that thinks the earth is warming? All right, well, the answer to that is we definitely found liberal Democrats that believe the earth is warming. This number is not 0. So that means that they do both occur at the same time, which means these are not mutually exclusive. So in a contingency table, mutually exclusive means there should be a 0 where that column and row intersect. It's also possible that, like, we could say, is believing the earth is warming and believing the earth is not warming. You know, well, those would also be, or those would be mutually exclusive, because you don't think the earth is warming and not warming at the same time. But in this case, since that entry isn't 0, we know that these are not mutually exclusive. All right, so let's go to here. So what is the probability that a randomly chosen respondent believes the earth is warming or is a liberal Democrat? Okay, so that or is super important, because now what we want to know is, as opposed to and, we don't have to be in the row and column in that one entry spot. Or is we can be a liberal Democrat, or we can believe that the earth is warming. So does anybody remember what we do for ors, how we calculate the probabilities of an or, P of A or B?
Don't you add one together with another and then minus another one?
Yep, that's exactly what, there are 2 that you add and there's 1 that you subtract. The 2 that you add are the probabilities of those 2 events. So in this case, it would be the probability that the earth is warming, which is this number right here, 0.6. And then we want to add to that the liberal Democrat, which is 0.2. So those are the 2 that you add. You take the 2 events that we're looking at and you add them together. And then what do we subtract? Oh, I see Ali put it in the chat box. Thank you. It's the probability of both of them. So in this case, it's the probability of someone who believes the earth is warming and is a liberal Democrat. And remember, for the and, that's the entry that's in the row and column that they share. So in this case, 0.18. So what we're going to do is we're going to take 0.6, we're going to add it to 0.2, and then subtract 0.18. And I believe, if I did my numbers right, that should end up being, oh, not 0262. All right, so it's going to be 0.62. All right, so that's how we do ors. You add up the 2 and then subtract what they share. Okay, so let's come down to part C. Part C says, what's the probability that a randomly chosen respondent believes the earth is warming given that he's a liberal Democrat? All right, so now with the givens, remember the idea behind the givens is we're not looking at the whole sample now. We're only looking at those that were of a certain type. In this case, that certain type is liberal Democrat. So we're going to ignore all of the things in the first 3 rows. I don't care about that. I only care about this row right here. So if we think about our total number of liberal Democrats, it's 0.2. We want to know how many of them were the ones that believe the earth is warming, which is 0.18. So I'm just going to type this in here as a division. so you can see what it's going to look like. I'll actually put in the real number in a minute, but it's going to be 0.18 out of 0.2 because we're only in the liberal Democrat row. Those that believe the earth is warming is 0.18 out of a total of 0.2. So if you do that division, you should get 0.9. So 90% of the liberal Democrats that were asked believe that the earth is warming. That's what this data tells me. All right, I probably should have mentioned this at the start. I don't want this to be political whatsoever because this isn't political. These numbers are all made up anyway, so I have no idea if this is true or not. It's irrelevant to what we're actually doing. So regardless of your feelings on global climate change or whether you're Republican or Democrat or otherwise, I don't really care. All right. Yeah, what about the libertarians? I guess none of them got asked, nor did any of the Green Party, nor did any of the Independent American Party or Communist Party, or insert your favorite other party there. Right? You can imagine how complicated this table could get, right? If we started including all that. So way too many lingering variables. But that's why this is just an example. All right, so let's look at D. What's the probability that a randomly chosen respondent believes the earth is warming given that he's a conservative Republican? Well, this is very much like question part C, except now we're going to be in just the conservative Republican row. I don't care about the rest of it. So I'm going to do the same thing that I did before, which is look at how many of those believe the earth is warming. Well, that was 0.11. Out of how many total are there? Well, the total number of conservative Republicans is 0.33. So I'm going to take 0.11 and I'm going to divide by 0.33. All right. So then this asks us to do this to how many decimal places? 4 decimal places. All right. So that's going to be 0.3333. All right. So what we can get from this, if these are actual numbers, this tells me that if you're a liberal Democrat, you're much more likely to believe that the earth is warming than if you're a conservative Republican. Only 1/3 of conservative Republicans believe the earth is warming, where 9/10 of liberal Democrats do. All right, at least from this sample. Okay, so in part E, does it appear that whether or not a respondent believes the earth is warming is independent of their party ideology? All right, so what do you think? Is it independent or dependent? Does it matter what party you are in terms of what your belief is on global warming? Well, it definitely looks like it's dependent because we're getting different numbers. Remember what dependent means? Dependent means that you're going to get, or independent, let's go independent. Independent means that the likelihood that it occurs overall is the same as the likelihood it occurs on a conditional probability, on a given. And you can see that that's definitely not the case. If we look overall, there's a 60% chance that people think, or there's a 60% probability that a random person chosen from this group believes that the earth is warming. But if we look at just liberal Democrats, that number is higher. If we look at just conservative Republicans, that number is lower. And so both of those suggest that this is definitely a dependent pair. The probabilities change. Okay, so, sorry about that. Getting freaking out there. Let's look at the last one. It says, what's the probability that a randomly chosen respondent is a moderate/liberal Republican, given that he does not believe that the earth is warming? Okay, so this is another given, but this time we're looking at the earth is not warming. So I'm looking at just this column. I don't care about the rest. I just want this column. So we're going to set this up the same way, right? We're going to take, see, out of all of these 0.34, how many of them are moderate / liberal Republicans? Okay, well, that's that second entry, which is 0.06. So the calculation I'm going to do is 0.06 divided by 0.34, right? There are 0.34 that believe in not warming, and of that, 0.06 are of the moderate / liberal Republican group. All right, so I went ahead and just did that division, and again, to 4 decimal places, I get 0.1765. So just about 17.5% are going to fall into that category. All right, so I'm going to go ahead and submit my question because I want to get some green check marks. Yes. Look at all the green check marks. All right, so hopefully this makes a little bit more sense with the, I know that somebody put in the chat box that they were, or maybe even said they were having trouble with the conditional probabilities, but maybe this makes a little more sense that when it's conditional, we ignore all the rest and we think about only those that follow that condition. And then once we've got that condition specified, we look in that smaller group, what portion of that smaller group satisfies the other event occurring. Whew. All right, so how are we on number 14? Feel better? Hopefully. Okay, so let's go look at number 17. So 17, same kind of deal. We've got pedestrian deaths that were caused by automobile accidents. And we have, were the driver intoxicated, were the pedestrian intoxicated, and we've got our numbers. So basically you read this like this 61 means that 61 of these deaths, overall deaths, occurred where both the pedestrian and driver were intoxicated. 227, the driver was not, but the pedestrian was. 71, the driver was, but the pedestrian wasn't, and so on. Okay, so if 2 different pedestrian deaths are randomly selected, find the probability that they both involve drivers that were not intoxicated. All right. So first question, is this sampling with or without replacement? All right, so I see a couple of withouts. Okay, this is definitely without replacement. And what about this tells you that it's without replacement? Good, it's that phrase, too different, right? It's different pedestrian deaths. So if we go and we pick person number 1, we don't put them back into the mix because we want a different person to look at. So now we're going to go reach in and get a second. So we're not replacing. All right. So what we're going to want to do is the same thing we did before, which is multiply them together and figure out what is the probability that occurs. So let me go to whiteboard because this one I'm going to have to definitely write some more stuff to get our values. So let me just go ahead and clear all this. Okay, so let me just replicate that chart real quick. So it looked like this, 61, 71, 227, 621. So this was the driver side, yes and no. This was the pedestrian bit, yes and no. Okay, and what we're looking for was the probability that neither of them involved an intoxicated driver. Okay, so it said we want to find the probability that they both involve drivers that were not intoxicated. Okay, so let's look at number one. So for person number one, the question is, what's the probability that the driver was not intoxicated? Well, in terms of the total number that were not intoxicated, let's actually kind of add to this chart. We're going to make some totals here. So the total number that were intoxicated is 132. We'll just add those together. And the total that were not intoxicated is 848. And if we look at the total, it's 980. So for the non-intoxicated, it's 848 out of 980. That's the probability that the first person we look at was an accident that did not involve an intoxicated driver. So before I move on, we good with number one? Give me a thumbs up if you're good on that. All right, cool. I'm seeing a couple of thumbs up. All right, so now let's go to number two. So person number two, remember now we need a different person. So there aren't 980 total that we're looking at anymore. Now there are only 979, right? Because we removed that one because we want a different person. Okay, so then the likelihood that they're from a non-intoxicated driver, well, that number we also have to reduce by 1. Because remember, the first one was a non-intoxicated driver. So that means out of those 848, there's actually only 847 left. All right, well, those are those two probabilities. And now we're going to go ahead and multiply them together just like we did before. So let me real quick see what that gives me. This ends up being 0.7486, blah, 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 or around 74.9%. So almost 75%, almost 75% chance that the accident did not involve an intoxicated driver. If we look at pull 2 out. All right, so that one, even though we had a contingency table, notice that we approached it completely different than the other one with contingency table because we were asked a different question. And that's why it's so terribly important to read the question and find out what they're asking. Okay, so I really can't stress that enough. All right, so let's go take a real quick look at number 29. And maybe today we'll actually do something new. We'll see. All right. So a bag contains 7 red marbles, 7 white marbles, and 6 blue marbles. You draw 3 marbles out at random without replacement. Key, without replacement. Find the following probabilities and round to 4 decimal places. Okay, so the first one is we want to know what's the probability that all the marbles are red, and then what's the probability that none of the marbles are red. All right, well, let's go back to the whiteboard and let's see what we can do with this guy. All right, so here's the important bits from this. We had 7 red, 7 white, and 6 blue. We're going to draw 3 without replacement. So I reach in, I pull out a marble. Hey, it's white. That white one's gone. Now I reach in, I draw another one, another one. Okay, so part A was what's the probability that all of them are red? So let's break it down like we did the first time. Number one marble. What's the probability that when we reach in, we get a red marble? Well, we need to know how many red marbles there are. There's 7 of them. And we need to know how many total marbles there are. Well, 7, 7, and 6 is 20. So there's a 7 out of 20 chance we reach in, we get a red marble. All right, but we want to keep going. What about number 2? Since it's not replacement, there are only 19 marbles left. And there aren't 7 reds anymore, there are only 6. And then similarly for number 3, there are only 5 remaining reds, and there are only 18 total marbles left. So those are the probabilities for the first one being red, the second one being red, the third one being red. And now we multiply those guys together. Okay, so if I, again, take my trusty calculator here and do that division real quick. I get 0.0307, or around, we'll round it to 1 decimal place on the percentage because that's what I like to do, 3.1. So it's very unlikely that we actually get 3 red ones. There's only slightly more than a 3% chance. Okay, so not very likely that all of them are red. The other one asks us, what's the probability that none are red? Okay, I want to warn you about something because I think some of you might already have an idea of what you think it is. If you think that it's 96.9, which is the 1 minus, that's actually not correct. Because the complement of all of them are red is not none are red, it's at least one of them is red. So the 97%, that's one of them was red, 2 of them are red, or none of them are red. So we have to be a little bit careful here. For none of them being red, we're going to do exactly the same thing that we just did. Where we're going to look at each draw and figure out what's the probability that each of these is non-red. So for the first draw, there are still 20 total marbles, but we're looking for how many of them are not red. And it turns out that there are 13 of them that are not red, because you got the 7 white and the 6 blue. Once we remove one of those, we're down to just 19 marbles, but now there are 12 that are not red. Right? So from 13 down to 12 because we took one of them out. And then the last one, there are now only 11 non-reds remaining. Again, I don't know if they're white or blue. I don't really care. I just care that they're not red out of those 18. All right. So again, we're going to go ahead and multiply those together. So let's go to my trusty sidekick here. And I get 0.2508 blah, 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 which is around a 25.1% chance. So there's basically a 1 in 4 chance that if we reach in and grab 3 marbles, that none of them are red, which is considerably different. But again, the key to this is without replacement. Because if we had had replacement, it would have changed these things considerably. All right, so okay for that one? All right, well, hopefully that definitely helps you with the whole idea of probabilities and what's going on. And you're in a good enough spot to finish off the homework for tonight. I know we've just spent a long time on that, but that's okay. I don't mind doing the review because we need to know how to do probabilities to deal with probability density functions. All right, but we're going to take a break because I need to stop talking for a little bit. Let's come back in 10 minutes at top of the hour. All right, so at 5 o'clock, I'll be up at the whiteboard. You're going to know that I'm ready to go because I'll turn my whiteboard back on. Right now the video is showing, but I will turn off that video. Oh, actually, look at that. I have the power. So you will know I'm back when the whiteboard pops up with me, but plan on that at the top of the hour. All right. So go to stretch, go use the restroom, grab a drink, whatever, and I'll see you guys in 10 minutes. All right, so we're back. We'll just get it out of the way. Star Wars shirt of the day. All right, so let's talk a little bit more about where we left off last time, which was looking at probability density functions. So let me remind you about those, and then we're going to look at some specific types. All right, so a probability density function, which from here on out, I'm going to call a PDF, is exactly what it sounds like. It's giving you the distribution of different probabilities, right? The probabilities that different things occur. And so it's sort of like when we had a contingency table or things like that. It's what is the likelihood that such a thing happens? And there are two types. There are continuous and there are discrete. And right now we're looking at discrete specifically. So the ones that we can actually count. So I showed you some examples last time. We talked about tossing a die, right? And all the different possibilities there. So like what's the probability, or tossing a die, tossing a coin. What's the probability of getting 3 heads if we toss 3 coins and that sort of thing. We looked at World Series, so on and so forth. But some characteristics of the probability density function that are really important, right? So some things to remember is that each probability is between 0 and 1. All right, so each individual possible outcome has a probability somewhere between 0 and 1. And the sum of the probabilities is 1. All right, so if we add up all the probabilities, we get 1, right? Whatever the event happens to be. So again, if you go back and you look, we did the ones with the World Series or the tossing of the coins. We know what those numbers are. All right, so there are lots of probability density functions. And it really kind of depends on what we're doing and what we're looking for. And there are a fair number of discrete probability density functions. And I'm going to show you 3 of them today. All right, we're actually going to look at 3 different probability density functions and how they behave and how they work. And then I'm going to talk about the technology that you need to use. So I'm going to kind of walk you through what you need to look for. If you look in the book and you've got a TI 83 or 84, 83 plus, 84 plus, it will tell you exactly how to do it. I'll give you the general, what you're looking for. So if you've got a different kind of technology, you can still find it. Right? Anyway, so here's the first of the discrete density, probability density functions I want to talk about. And this one's called a binomial PDF. Okay, so it's a binomial probability density function. All right, now the deal with a binomial distribution is that there are only 2 possible outcomes. Now I'm going to put here per trial. All right, so only 2 things can happen. That's why it's called binomial. Bi is a prefix for 2, right? Like think about bi, right? Biplane, biped, bisexual. Like bi means 2, right? So binomial, 2 options. These are the kinds of things where it's yes or no, right? You go ask somebody a question. If that question can be responded to as yes or no, it's binomial, right? So for example, if I were to go out and ask you what eye color you have, that's not going to lead to a binomial distribution because there's more than one option. Blue, brown, green, hazel, right? Like we have all kinds of different options. But if I were to ask you, do you have brown eyes? That one, there are only two possible responses. Yes or no. Right? So a binomial distribution comes from something that we're looking at where there are only two possible outcomes. Okay, so that's the first thing that's kind of important here. What we need to know when we're doing a binomial PDF is two things. So if you're going to set one of these, a binomial PDF up, you need to know two things. The first is how many trials, right? So how many people are we actually asking? Let's go to that brown eye question. So if I go out and I ask 20 people, that's 20 different trials. Each person is a trial, right? I'm asking, do you have brown eyes? Yes or no? Okay, that's one. Do you have brown eyes? Yes or no? That's my second trial. Do you have brown eyes? Yes or no? That's my third trial, and so on. So you need to know how many trials are going on. And you also need to know what's the probability of a success. Now I'm going to put success in quotes. In that context of a yes/no question, maybe you want to say a success is a yes response. You can also say it's a no response. It doesn't really matter. But you have to decide, what does it mean for a success? What does it mean for something to be a success? And what's the probability? All right. So let's say I'm tossing a coin. And I'm going to say that a success is if I get ahead. All right, so then my probability of success, the probability of getting ahead, is 1/2. Let's say we're rolling a die. Roll a 6. The probability of rolling a 6 is 1 in 6. So if I say that a success is rolling a 6 and a failure is anything else, then that one, the probability of success is 1 out of 6. Maybe I already know that out there in the world, the probability that somebody has brown eyes is 60%. Completely random. I have no idea if it's 60%. But let's just say that the probability that someone has brown eyes is 60%. If I define a success as you telling me you have brown eyes, then that probability is 0.6. All right, so you need to know both of these things. So you can define a success however you want. Just make sure you have the corresponding probability for that success. All right, so we need to know those two things. And then the last thing that's important with a binomial PDF is that each of these trials has to be independent. And again, remember, independent is the result of one doesn't affect the result of the other. And in the example of me and just going and asking people what their eye color is, those are going to be independent, right? Because if I go around and I ask Tassel and he gives me his answer is not going to impact Kira's. It's not, right? It's not like Kira's going to go, wait a minute, Tassel says he has brown eyes. I don't want to say the same thing as him, right? No, that's not going to be the case, right? It's not like Tassel telling me what color his eyes are is going to change Kira's eyes all of a sudden. At least I don't think so. That'd be pretty cool, Kira, if you had that power. You got a little X-Men in you that I don't know about. So it just has to be something that's independent. And in this example, they're definitely independent. All right, so this is what we need for a binomial PDF. All right, now, in terms of probability density functions, there are a lot of things that we want to be able to do. First, we want to have a notation for them. For the binomial, the notation that we're going to use, we're going to have our capital X. You may remember that that's the variable. We put a little squiggly thing here called the tilde. And then we put a capital B, or binomial. So we have capital B, and then in parentheses, we're going to put N, comma, P. All right, so again, N, this is your number of trials. P, this is the probability of the success. And so what big X is, this is a measure of the number of successes. So remember that the variable is always, it's something that we're keeping track of, right, that we're measuring. In this case, it would be the number of successes. So the binomial distribution is going to give you the probability of a certain number of successes. All right, so go back to that example. Let's say we're doing eye color. All right, so I'm just going to say, let's say that it's 60% chance. We know that the probability is 0.6 that someone has brown eyes. Okay, and we're going to go ask 20 people the question, do you have brown eyes? So this would be binomial, because there are only two possibilities, yes or no. So we're going to write X tilde B, so binomial. And this is going to be 20 comma 0.6. All right, so that's going to be the notation. Now, we could actually do the same thing if we wanted to know if they don't have brown eyes, if we wanted to have our success be an answer of no to this question, that's fine. The only thing that would change is this wouldn't be 0.6, it would now be 0.4. Because the probability that you say no is 1 minus the probability you say yes. All right, so that's the kind of notation we're going to have for something that's binomial. All right, so obviously we now have some questions that we probably want to answer regarding this. One is maybe what's the mean of this distribution? What's the average number of successes? We probably also want to know the standard deviation so that we can compare if we get some really weird number of yeses, of successes. Oh, was that normal or not? Was it usual, expected, whatever? So we probably want the mean, the standard deviation. And then we also want to know what's the actual probability for different outcomes. All right, well, let's start with the mean and standard deviations. There are formulas for mean and standard deviation with the binomial PDF. And they're pretty easy. Well, they're easy to describe. But first, the mean. So we're going to use mu, because this is a population mean, right? And the mu, it's equal to n times p. So it's really easy to calculate. All right, so what's the average number of successes? You just take your mean, or sorry, your n, your population, your sample size, and multiply by the probability of a success. So like with this one, if it really is a 60% chance that someone had brown eyes, the mean number would be 20 times 0.6 or 12. So I should expect, on average, if I go out and I ask 20 people, do you have brown eyes? I should expect 12 of them will say yes. Now, will it always be 12? No. Sometimes 11, sometimes 19, sometimes 2. But on average, over the long haul, if I ask lots of groups of 20, on average, I should expect around 12 responses of, yes, I have brown eyes. All right, so that's the mean of the binomial PDF. And the standard deviation, again, it's a population standard deviation, so it's a sigma. It's the square root of m times p times q. Now, where that formula comes from, just smile and nod. Just go, okay, yeah, that's it. For all these distributions, there are reasons that these formulas come about. I don't want to get into that. This is an introductory to stats course. This is a how do we use it, not where it comes from. If you want to learn about where it comes from, you can take classes on it. I'll just tell you that I took a class called Probability and Statistics as a math major. It was a 400 level class. So it was a senior math major class. Not a lot of people take that class, but that's where you learn all the whys, right? But for you guys to be able to use it, you don't need to know where that comes from. You just need to know that it is it. All right, so that's your mean and your standard deviation. So this one also not super complicated. It's a little bit more difficult to calculate, but it's just a matter of putting in N, P, and Q. But now you might be wondering, what's Q? All of a sudden, there's this new random thing here. Well, Q, this is actually 1 minus P. If you want that in words, Q is the probability of failure. So if P is the probability of success, Q is the probability of failure. Okay, so let's look at this binomial and let's actually write down what all these different things are then. So if we're looking at a binomial distribution where we're asking 20 people and the probability of success is 0.6, the mean then is going to be 20 times 0.6 or 12. The standard deviation is going to be the square root of 20 times 0.6 times 0.4. Right? So the 0.4, that's the 1 minus 0.6. So I didn't run the numbers on this before. Let me do that real quick. So we'll take the square root of 20 times 0.6 times 0.4. And I get 2.19. Okay, so again, remember what standard deviation is telling us. This is telling us the spread. And in general, from Chebyshev's rule, we know that if we go 2 standard deviations on each side, we have at least 75% of the data is going to fall in there. If it's more symmetric and centrally located, 1 standard deviation or 2 standard deviations brings up to 95%, right? That's the empirical rule. But even with Chebyshev's, we know that if we were to go 4 on either side of the mean, so between 8 and 16, we should expect at least 75% of the responses. 75% of the time, we should get between 8 and 16 people saying, yes, we have brown eyes. So that should happen 75% of the time. So that's what sigma Standard deviation is telling. All right, so now the question is, what if we want to know the probability of a specific event? All right, so for example, let's keep doing this brown eye thing. So here's my question. What is the probability that 10 people of this group of 20 have brown eyes? Right, so I mean that's a typical kind of question. You say, okay, I'm going to go ask 20 people, do you have brown eyes? What's the probability that half of them do? What's the probability that exactly 10 of them have this? All right, now this is where we're going to use our technology, because there is a formula to find this. It's a pain in the you know what. All right, so you don't want that. Instead, you want to use your technology to help you. All right, so what you're going to be looking for, no matter what kind of technology you've got, what kind of calculator, computer, whatever, you're going to find, you need to find a stats menu. Okay, now where your stats menu is, I can't really tell you unless I know exactly what you're working with. Like with my TI-89, I have one it's called like stats data list or whatever, and I go and put it in. But what you want to look for is something that says distributions or dist. It's often under something, a window that says tests or something, but you want to look for something that says distributions. And in that distribution list, you're going to see a ton. Let me hold mine up. See if you can see it a little bit. It's kind of dark. I don't know if you can even read that. No, it's completely out of focus. But anyway, there are all kinds of lists, things on here. There's one that's called normal. There's one that's called T. There's one called chi-square, geometric, Poisson, binomial, F, chi-square. Right? There's a ton of them. But for each one of these, there are also, they're actually paired together. All right. So what you're going to look for is something that says binomial PDF, and there's also going to be something that says binomial CDF. So any kind of distribution, there should be two, one that says PDF and one that says CDF. So there's going to be one that says normal PDF, normal CDF. There's going to be chi-squared PDF, chi-squared CDF. We're going to see all these distributions as we go. But there's a huge difference between PDF and CDF. You use the PDF command. This is for the probability of a specific value. All right, so like with our example here, we're trying to find out how many have 10, or how many, a probability of getting 10 people say they have brown eyes. That's going to be PDF because we want to know exactly 10. For CDF, this is the probability of less than or equal to a specific value. All right, so this would be, what's the probability of 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10? Okay, so we're adding up. And that's what this C means. This C stands for cumulative, or added up. All right, so if you want to know a specific value, use PDF. if you want to know a range of values from 0 on up, that's CDF. So for this specific one that I just said, like what's the probability that 10 of this set of 20 have brown eyes? The command I'm going to want to use, and again, your technology, it might look a little bit different, but it's going to be something along these lines. I'm going to want to do a binomial PDF. Okay, so this one's going to lead to a PDF because I want an exact value. If I were to write this with probability notation, I'm looking for what's the probability that my variable equals 10. What's the probability that the number of people that with brown eyes is 10? So equals leads to PDF. Now, it's pretty standard when you have PDF. When you do this command, it's going to ask you for N and P, right? So you're going to need to know N and P, and then the number that you want. So for me, or for my command, or for this specific one, we're going to do binomial PDF 20, because we're doing 20 attempts, 0.6, because brown eyes is 6% or 60% likelihood. And I'm going to look for exactly 10. All right, now I'm going to go ahead and calculate this using my calculator. And then this way you can go back once you figure out how your technology works. And you can plug in these numbers and see if you get the same thing. All right, so my calculator thinks for just a minute. And it tells me I have 0.11714, blah, 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 blah. All right, so once you get your technology, put it in, see if you get that number. If you don't, contact me. We can work during office hours and we can figure it out. All right, but let's interpret this. What does this mean? This means that 11.7% of the time, so 11.7% of groups of 20 will have 10 brown-eyed people. Right, so around 11.7% of the time, a group of 20 people will have 10 brown-eyed folks. All right, so that's the interpretation there. Now, this number is actually pretty big. I know you might not think that 11.7% is very large, but that's a pretty big number when it comes to this. But that's because this 10 was close to the mean. Remember what the mean was? It was 12 in this case. So getting a number like 10, which isn't very far from 12, is pretty reasonable. Let me show you how much this changes if we go far away from the mean. So let's, instead of looking at 10 people, what if instead it's only 5 people? So what's the likelihood that if we grab 20 people and we ask them, do you have brown eyes? Then only 5 of them have brown eyes. Okay, well, I can use the exact same command. I'm still going to do binomial PDF because I want exactly 5. I still have 20 trials. I still have a success percentage or a probability of 0.6. But now I'm looking for just 5. So it would be 20, 0.65. So I change that on my calculator here and I run the numbers. And so let me go ahead and write this up here. So binomial PDF of 20, 0.6, 5 this is 0.00129 blah, 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 which is around 0.1%. So not just 1% of them, but 0.1%. So basically this is saying that 1 out of every 1,000 groups of 20 people would be such that only 5 of them have brown eyes. So that's a much less likely occurrence, but that's because 5 is very far from the mean, right? We should expect on average 12 people saying they have brown eyes. Getting only 5 is unlikely. Okay, so that's how PDF works here. This is going to give us what's the probability that we get that exact number of successes. In this case, people responding, yes, I have brown eyes. All right, now remember how I said a little bit ago, wording is supremely important. That's the case specifically with CDFs. All right, so let me just first give you some mathy notation to let you know how these things work. But then we'll talk about what the words mean. So again, when we had PDF, we use that when X equals a number. All right, so I'm just going to put 10 there, but it could be X equals 4, X equals 3, whatever. The CDF command that gives you less than or equal to 10. So what this would account for, like in our specific scenario, would be how many of them have are such that there are 0 people with brown eyes. And what's the probability that there's 1 person with brown eyes? And what's the probability of 2 and 3 and 4, all the way to the probability of 10, and we add them all together because it's cumulative. All right, so that's the big difference. PDF is the 1 value, and CDF is everything less than or equal to that value. All right, now, this is great for those, but let me show you what you have to do if you want other kinds of probabilities. Okay, so if you want the probability that say X is greater than 10, we don't have a command to do that. So what we have to do is recognize that this one is the complement of less than or equal. This is everything else. And the way we get complements, probabilities, is by subtracting from 1. So this guy, this is going to be 1 minus CDF. And I'm going to put 10 in parentheses just because we're dealing with the number 10. So CDF of 10 gives us the probability of less than or equal. So greater than is 1 minus that. All right, well, another probability we might want is instead of less than or equal, what if I just want strictly less than? So I don't care about 10. I only want to know 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, well, there are 2 ways to think about this. One is we can do CDF 10 minus PDF 10. Because remember what PDF 10 was? That's the probability of having exactly 10. Well, if I take that away, now I have everything up to including 10, but not 10. I like to show you this one because this is how we're going to do it when it's a continuous density function, probability density function. Because this is discrete, we do have an alternative way. So I am going to put this as an or, but this is only because it's discrete. We could do CDF of 9. So think about what CDF 9 means. It's going to be probability of 1, 2, 3, 4, 5, 6, 7, 8, and 9, including 9. Which is what it means if we're less than 10 and we're counting, right? Discrete, we're counting. And so since we're counting, the biggest number less than 10 that we can count is 9. But I'd rather you think of it this way, as CDF minus PDF, because that's going to be what we do when we get to continuous. All right, so the only other one that remains that we haven't talked about yet is what about greater than or equal? So what if it's greater than or equal to 10?
You'd include 10.
I'm sorry, can you say that again?
You didn't include 10 in the range.
So now we want 10 in there, yeah. So there are a couple of ways we can approach this. One, and this is how I want you to think about it just in general, because this will, again, work for a continuous, is we're going to do the not 10. So it's going to be 1 minus CDF of 10, right? So that's the greater than 10. But then we need to add on 10. So the first bit, this guy, came from up here. That was the greater than 10. And then this is the equal to 10. But again, because this is discrete, we could also do this as 1 minus CDF of 9. We can take 1 through 9 and eliminate those. Wow. So you're already starting to see that this can get complicated depending upon which different kind of probability we're trying to do. And if you're at the point where you're already like, oh man, I'm screwed, I hate to even throw this at you. These are going to be coming from word problems. And we're going to have the words tell us which of these we want. So let me talk about some of the phrases you're going to see and which ones they translate to, which of these translate to. All right. I also want to make very clear the 10 is just an example number. It can be any number. And we're going to follow the same kind of idea. I'm just using 10 because that's what we were talking about. Okay, so here are some of the phrases you're going to see. Right? Obviously, think of things like less than, more than, and so on, right? Those are pretty easy to tell because that's exactly what inequalities tell you. So if we say, what's the probability that x is less than 10? Yep, that's that guy right here. What's the probability that x is greater than 10? That's this one. All right, so those I think you probably know pretty well. But here are some that are a little bit more difficult to interpret because it's not just automatically a less than or greater than. Right? So how about this one? At least 10. Let's just say we've got at least 10. So what's that inequality going to look like?
Would that be less than or equal to?
Okay, it would actually be greater than or equal if we're going to say we're at least 10, because that can be 10, 11, 12, 13, and so on. So that one's greater than or equal to. there's also no more than. What's the probability that we get no more than 10? Ooh. I didn't catch who just spoke out there, but whoever that was, if you just said it again, now you'd be right. It's x is less than or equal to 10. Because if you're not more than 10, you're not 11, 12, 13, 14. So it's anything up to and including 10. At least 10, no more than 10. And of course, it goes on and on and on. But these are some of the more common ones that you're going to see. So you got to figure out which of these scenarios you're in so that you can do the right commands on your calculator to get the right probabilities. And this is when students start hating statistics, right? If you weren't already there, this is when people really start not liking it. Because A, it's word problems. B, depending upon what we're doing, we have all kinds of crazy things that we have to try to keep track of. And C, we have to interpret the word problems that tell us which one it is. Like, it can get really complicated. So my best advice with these is practice them. Practice, practice, practice. Read them. Start learning what the different phrases mean so that you can actually start getting the right values. Also, as you practice them, if you're having trouble, get help. Come find me in an office hour, find the tutors, right? So that we can help you out. All right, so these are the setups for these. So let's try another one here real quick. Let's completely change what we're doing. Let's go to, we're tossing a coin 4 times. Okay, so we're going to toss a coin 4 times. And let's see if we can calculate the following. All right, we'll just do this one. So toss a coin, a fair coin, 4 times. What is the probability that you get at least 2 heads? All right, so here's our goal. Let's see if we can figure out what's the probability of getting at least 2 heads if we do this. Okay, so first, here's the binomial distribution we're using. It's binomial because there are only 2 options each time. I toss the coin, it's either a heads or it's a tails. Right? Think of it as the question, did you get a heads? You either answer yes or no. So it's binomial. All right, so the number of trials is 4 because we're tossing the coin 4 times. Our probability of success, if we say success is getting ahead, is 0.5. 50-50 shot. Okay, so this is the distribution that we're using. All right, but what is our probability? What are we actually trying to determine? Well, we're trying to find the probability that we get at least 2 heads. So what should I put in here with my X? I'll put in this part. I know there's a 2 because we're comparing it to 2. But what goes in here? Equals, greater than, less than, greater than or equal, less than or equal.
Greater than or equals.
Good. It's going to be greater than or equal. Because we want at least 2 heads. So they can be 2 heads, 3 heads, or 4 heads. Okay, so I'm going to do this the fast way since this is discrete. I'm going to take 1 and subtract the complement of this. So greater than or equal to 2, the complement is less than 2, which means that's either 0 or 1. So that's going to be a cumulative. So I'm going to do the CDF of 1. CDF of 1 means that's the probability of getting a 0 or a 1. But I'm going to remove those because I want the other one. Okay, so this is what I'm going to do to actually calculate that value. All right, so I'm going to go to my trusty calculator here. We're going to do, again, binomial. I'm going to do binomial CDF. I'm doing 4 trials. The success rate is 0.5, so 50%. All right, so then my CDF, I'm going from 0 to 1. All right, so I calculated that my CDF is 0.3125. So I'm going to subtract that from 1, and I get 0.6875. All right, so the probability that I get at least 2 heads is 68.75% of the time. Boom. All right, so that's the likelihood that that will happen. Now, I could have actually figured this out using like a tree diagram. Remember when we did that with our heads and tails and we figured out all the different probabilities of the different ones? I could have done that to get this, but it's a lot faster to use my technology. So I highly recommend that, especially if you have lots of trials. Like imagine we were going to toss a coin 10 times, 20 times. That tree's going to get huge. And I don't want to do that, right? So this is definitely a little bit easier. All right, well, anyway, so there's your binomial distribution. 2 things can happen, yes or no. All right, so the next one I want to show you is what's called a geometric distribution function. All right, so first of all, in terms of the notation for this, we're going to have X with the tilde, but this time we're going to have a capital G for geometric. But for geometric, you only need to know one thing, and it's a probability. Okay, so what this P is, again, just like before, this is the probability of a success. All right, so it's a successful outcome of whatever we're doing. Right? So it could be someone saying they have brown eyes or whatever. But how a geometric distribution works, what X is, this is the number of trials until success. So let's go to the tossing of the coin. All right, so what I'm going to do is I'm going to figure out on that, you know, like how many tosses do I need until I get a head? All right, so here we go. I'm going to do this experiment right now. So here's a penny. We got a heads, we got a tail. You can just trust me that I'm not lying here. So I'm going to go until I get a head. All right, I got a tail. That was 1 attempt. Tail, 2 attempts. Tail, 3 attempts. Oh my gosh. 4th attempt, tail. 5th attempt, tail. I swear this is an even coin. All right, finally ahead.
I was gonna say.
I know, right? So that was 6 times, 6 tosses. So in this case, X would be 6. It took me 6 tosses to get ahead. All right, so now I'm going to start over. Do it again. Toss it, you get a tail. Man, this coin likes tails for some reason. There's a tail. There's a tail. Oh my God, 4, 5. I am flabbergasted. Okay, so then 6, another 6. Tail. What the hell is up with this coin? All right, so that one took 3 tries. So that would have been X equals 3 and so on. So if I happen to go first time and get ahead, ooh, I did it that time. That's 1 try and so on. So is everybody kind of cool with what X means? It's how many times does it occur? How many times did you have to go until you got success? The fact it took me 6 times twice is pretty rare. Pretty rare. All right, well, geometric distribution calculates this. All right, so for these, it's the same kind of deal. If we have a PDF, that's the probability of exactly that number, right? CDF would be cumulative, adding up to that point. All right, so for this one, if we look at mean, standard deviation, and so on, this is what you get. The mean is 1 over p. So it's just 1 over the probability. That's on average how many times you need to do it before you get success. The standard deviation is a little bit uglier. It's still kind of like with the binomial. It's a square root 1 over p, and then 1 over p minus 1. So that's how you can actually calculate the standard deviation for something like that. So let's look at tossing the coin, right? So with that example where I was tossing that penny, we're looking at G of 0.5. So you know, so all it depends on is the probability, because now we're waiting for the number of trials. We're trying to calculate that. So in this case, the mean is going to be 1 over 0.5 or 2. So we should expect on average that it takes 2 attempts to get ahead when we're tossing coins. So if we get a number that's near that, like 1 or 3, that's not all that uncommon. The further away we get, the more unlikely it is. So like the fact I had to go all the way to 6 was pretty incredible. All right, well, here's your standard deviation. So it's going to be the square root of 1 over 0.5 times 1 over 0.5 minus 1, which is the square root of 2, which is 1.14 something or other. No, 1.42. 1.41 something. It's around there. Okay, so again, think about what standard deviation tells you. If we go 2 standard deviations on each side, we catch 75% of them. So 75% of the time, at least, we should get a number between 0 and 4.8. 0 and 5, basically. So that's what this number is telling me, just from Chevy-Chevs, is that 75%, at least 75% of the time, it's going to be accomplished between 0 and 5. Now, my samples don't back that up, right? Like, I think I did it 4 times and twice it took me 6. But remember, that's a really small number. And when we talk about standard deviation and means and all that, that's lots and lots and lots and lots of trials. All right, well, let's actually calculate now the probability that it took me 6 tries. Okay, so we're going to do this. We're going to calculate geometric PDF, where our probability was 0.5, and I'm looking for 6. Okay, so this is going to be the probability that it takes 6 tosses to get your first head. All right, and again, that's what geometric does. It's how many times do you have to do it until you're successful. All right, so let's go see what this happens to say. All right, so I'm going to do a geometric PDF. The probability of success was 0.5. And I want to know how long it's going to take, or what's the probability that I have to go out to 6 trials. All right, well, my calculator spits out, oh man, this is not very likely. 0.015625. Oh, I need one more 0. So only about 1.6% of the time do you need to get to 6 tosses before you get your first head. And I did it twice in a row. Holy cow. This is definitely the day I need to buy a lottery ticket because weird stuff's happening. All right, well, that's your geometric distribution. I wanted to show you another one, but I see we're out of time. So I'm going to save the Poisson distribution for next time, for Thursday. So again, just reminding you, no quiz Thursday. No quiz Thursday. We're starting class at the regular time, 3:30. All right. We're going to hit Poisson distribution, and then we'll start looking at continuous distribution functions. And specifically, I think we're going to be looking at what we call the normal. All right. So no quiz on Thursday. We're just doing regular stuff. And the reason there's no quiz on Thursday is because it wasn't scheduled that way. But remember that even though the schedule says project 1 is due Thursday, it is not. I extended it to Tuesday. All right. So you got a couple more days to work on that. Make sure you get out there and give me a good project. All right. So with that, I'm going to go ahead and stop our recording.